Let's talk a bit about the nucleus. Now, you probably learned these terms early on, especially if you've had a chemistry course or a physics course in high school. But to make sure we're all on the same page, the atomic nucleus, so all atoms have a nucleus. Those nuclei consist of protons and neutrons. So protons are positively charged particles found in the nucleus. Neutrons are neutral particles found in the nucleus. Collectively, all of these things together are called nucleons. So a nucleon refers to a proton or a neutron. It refers to a particle in the nucleus. Electrons are not nucleons because they are not found in an atomic nucleus. Now, neutrons are slightly more massive than protons are, but both are significantly more massive than electrons, about 1,800 times or 1,800 times more massive than an electron, roughly, which means that the vast majority of mass in an atom is in the nucleus of that atom. The electrons make up a very small fraction, far less than 1% of the mass of an atom. So to measure masses in atoms or in nuclei or in molecules and so on, kilograms are just too big, right? Kilogram is a wonderful, useful mass measurement on the macroscopic world, the world that you and I live in. But when talking about individual atoms or the nuclei within those individual atoms, it's way too big. So we talk about a unit here called the atomic mass unit, which is represented in your textbook with a lowercase u. Some places abbreviate it AMU and use all three letters, but we're just going to use the lowercase u, where one atomic mass unit is equal to 1.6605 times 10 to the minus 27 kilograms. It turns out a proton is about one atomic mass unit. A neutron is about one atomic mass unit. They're not identical to one atomic mass unit, but they're approximately one atomic mass unit, which is why that scale is chosen. Now, alternatively, rather than talking about nuclei or neutrons and protons in terms of their mass, we can use Einstein's equation, E equals mc squared, which we learned about in the relativity chapter, to talk about the mass in terms of mass energy, right? So basically, solving this equation for m is equal to the energy over c squared. So one atomic mass unit is 931.5 million electron volts, or MeV, over c squared. And again, c squared is just the speed of light squared. It's a constant. This is useful because it tells us approximately how much energy one atomic mass unit has. So when a nucleus loses a little bit of mass during nuclear fission or nuclear fusion, which we'll talk about later on in the next lesson, we can talk about how much mass is lost, lets us know how much energy is lost. So the process of nuclear power is when you break up large uranium molecules or uranium atoms into smaller products, or when you fuse hydrogen atoms into helium, energy is lost. I'm sorry, mass is lost. That mass is converted into energy using this relationship. So how do we write a nucleus? How do we talk about what specific type of nucleus we're referring to? Now, atomic nuclei being composed of protons and neutrons, that means that if you have a different number of protons and a different number of neutrons, you have a different atomic nucleus. Well, how do we know which one we have? How do we make the notation that explains to the person who's reading it what nucleotide we're dealing with? Well, a specific combination of protons and neutrons is called a nucleide and is a unique nucleus. The following notation is used. So we have four different things. X is just a symbol for the element. For example, hydrogen is capital H, helium is capital H, lowercase e, carbon is C, oxygen is O, neon is capital N, small e. So there's a one or two letter designation that tells you what element you're dealing with. Once you know the element you're dealing with, you can write down right away Z, the atomic number, which is the number of protons in that nucleus. Those two things are redundant. Hydrogen has one proton. Helium has two protons. Lithium has three, boron 4. or beryllium 4, boron 5, and so on. You have oxygen with 8, nitrogen with 7, carbon with 6, and so on. Carbon always has 6 protons. Carbon cannot not have 6 protons. If it has 7 protons, it's not carbon, it's nitrogen. If it has 8, it's oxygen, right? So Z and X here are redundant. If you know one, you know the other. If I know this is carbon, Z has to be 6. If I know Z is 6, the symbol has to be that for carbon. Then you have A, which is the mass number. A is the total number of nucleons in the nucleus. So it's the number of protons plus the number of neutrons. And a rule of thumb is, at least at low atomic number, the protons and neutrons usually are close together in number. They're almost matching. Carbon, for example, carbon with 6 protons and 6 neutrons, 6 plus 6 is 12, so the mass number would be 12, and it would be referred to as carbon 12. As opposed to carbon 14, which you might have heard is radioactive, carbon 14 or carbon 14 dating, radioactive carbon dating uses carbon 14. Carbon 14 has 14 atomic mass number, which means that if 6 of those are protons of those 14, 8 have to be neutrons. And then finally, the last number here, N, is the neutron number. How many neutrons are in the element, or in the nuclei? So some of this is redundant as well. If you know A, which is the mass number, and you know what the element is, you can figure out how many neutrons there are. Or if you know the number of neutrons and the number of protons, you can just add those two things together to get the atomic mass. So writing it out fully, carbon 14 would look like this. Here's carbon, has 6 protons, that's why it's carbon. Atomic mass is 14 for carbon 14, so 8 of those nucleons must be neutrons, right? 6 are protons, 8 must be neutrons to get carbon 14. Well, that's redundant, right? Because we know 14 minus 6 is 8. Since we have 14 and 6 here already, often you don't write the number of neutrons, you just write carbon 14 like this. Because you still know how many neutrons are in this because you just subtract the mass number by the atomic number to get the number of neutrons. And as I said before, the number of protons in the chemical element is redundant. So often you don't see the atomic number, you just see carbon 14 written like this. 14 nucleons, carbon. You can get all of these values from just these 2 bits of information. So this is often how things are written. I'll be a little more explicit in homework, and your book does a little more explicit writing things like this. Often the full set of 4 numbers is not used. Additionally, your book talks about the size of an atomic nucleus. Nuclei are incredibly small, much, much, much smaller than an atom. To give you a sense, if you go to a football stadium, if the football outer part of the stadium is the electron cloud, then the nucleus is usually, maybe a baseball or a smaller grape sitting, floating in the middle of the field. Most of an atom is empty space. The approximate radius of the atomic nucleus depends on how many nucleons are in it, right? More nucleons, you would assume the bigger the radius. So the nuclear radius is approximately equal to this value R0, which is 1.3 femtometers, 10 to the minus 15 meters. So even smaller than a picometer, much smaller than a nanometer, 1,000,000 times smaller than a nanometer. You have a femtometer times the mass number, A. And A is not atomic number, it doesn't start with atomic number Z, the mass number is A. The mass number to the 1/3 power. And that's just because the 1/3 power is because it's a 3-dimensional construction, so the radius goes as, the radius of a sphere, goes as r cubed, so therefore the volume goes as 1 over, the radius goes as 1 over the volume, cube root of the volume. So the mass number raised to the 1/3 power. So different configurations are possible for different elements. We call these same elements with different numbers of neutrons, we call these isotopes. Isotopes, carbon-14 is an isotope. Carbon-12 is an isotope of carbon. You could have technically carbon-13 or carbon-15. Why don't you have those? Well, they might be highly radioactive. So as you get to bigger and bigger atomic numbers, you need relatively more neutrons in a nucleus to make it stable. So unlike carbon-12, which has the same number of neutrons and protons, or helium-4, which has 2 protons and 2 neutrons. Oxygen-16, which has 8 protons and 8 neutrons. As you get more massive, you need relatively more neutrons than protons to hold the nucleus together. Remember, protons are all positively charged, so in the nucleus they hate one another. They want to repel one another. Neutrons think of as the glue that holds the nucleus together, the positive charged protons together. So when you get a lot of positive charges in there, very high atomic numbers, a very high number of protons, you need respectively more neutrons to make that stable. And eventually, very high atomic number elements, the elements we're discovering, berkelium, einsteinium, those very high atomic numbers, none of those are stable. They're all radioactive. So here's a table, a chart that shows you atomic number versus mass number. And you can see a 1-to-1 relationship in the middle, but see how as Z gets bigger, A gets much larger, faster. The trend of stable nuclei swings towards bigger mass numbers for a given atomic number. So not all elements have a stable isotope. Gold, I think, only has 1 stable isotope. And there are some elements with multiple stable isotopes, and many elements with multiple unstable isotopes. Those unstable isotopes are the ones we're interested in this section. What happens if an isotope is unstable? What happens to this nuclide if it gives off an alpha particle, or it gives off a beta particle, or a gamma particle? How does this nuclide change? And we'll explore that in the next bit of this lesson.